Hello, welcome to the demonstration corner. Today we're going to talk about the MP-1 with the transient plane source method and the technology we've developed for measuring thermal resistance with the transient method and all the advantages and capability across that with two modules. But before we do, as tradition here, we are going to look at the instruments that are available in the demonstration corner and talk about them and come back to the MP-1. So, on this side is our thermal resistance side, but steady state thermal resistance. So this in particular is a good introduction of two basic approaches that are important to the, almost like a segue into what we do with transient and why they're different. These are fantastic methods. They have many advantages over any transient method in unique situations. We're happy to talk with you about that, and it's an important conversation. So this is our GHFM01 or our guarded heat flow meter 01. It follows ASTM E1530. It has plate temperatures of -20 to 310 Celsius. It works off the principle of one-dimensional heat flow achieved by a guard wrapping around the sample where there's a delta, and you have very little delta of temperature laterally, so your heat is forced one-dimensionally. Why is that important? If you're measuring complex materials, what are complex materials? They're either heterogeneous or they're layered in a non-repeating way. Non-repeating meaning one layer individually different from the rest, or a combination of layers that are not repeating throughout. Those can only be measured by thermal resistance. So highly heterogeneous or heterogeneous materials or non-repeating. Those are true definitions of complex materials, that this has unique capability. One of the questions I get asked often is, what is heterogeneity? And it's not what you see under a microscope in terms of distribution of particles or porosity. It is in fact defined in terms of heat transfer materials. It's defined as how uniform or how homogeneous is the heat of travel, the travel of heat through your material in relation to the property of measurement. So let me rephrase that. The homogeneity in terms of heat transfer materials is in terms of this property or measurement properties are when you introduce heat, whether it's from a sensor or from an application, how uniform is the diffusion of heat. If it's not uniform, then it is not homogeneous in terms of thermophysical properties. So this method is quite important. This can measure thin films as well, as defined by the standard. The thin film approach to this is to layer several layers to a minimum layer, measure that, and then layer more layers to a second minimum thickness, and then more layers to a third minimum thickness. That's all captured, it's well defined and published. It works quite well. Obviously, each of these measurements can take time, and it does present some complexities, but it's one of the capabilities. I mention that because it does tie into what we're going to talk about. So it's a very important method following ASTM E1530. The other method that is similar to that we'll be mentioning today, it's similar in concept, that's steady state, is ASTM D5470, which is more focused on electronic materials or materials used in electronics, such as interface materials, thermal interface materials, and thin films, etc. Typical sample size is 2 inch, which is a fixed dimension. The thickness can vary from sub-millimeter up to 25 millimeters thick. So it's a very unique instrument. This is our GHFM01. The other steady state method that measures thermal resistance and calculates thermal conductivity from that is our heat flow meter. So this is for measuring insulation and construction materials. I should say the thermal conductivity range for the GHFM01 is from 0.1 watt per meter Kelvin up to 100 watts per meter Kelvin. So it is specifically designed for conductive materials, and that's where that guard is rather critical. This works off the principle of the typical materials that are used in insulation and construction are heterogeneous in nature. Whether they're repeating layers or not repeating layers, anything you can put into that in between these two plates, you're going to get a thermal resistance value with a measured thickness. Both instruments measure thickness and output thermal conductivity. This is the HFM100, so that defines the 100 millimeters as its thickness. The plate temperatures on this are -20 to 75 Celsius. There's a high temperature version of the HFM100, which is -30 to 110 Celsius. There's one other size of our HFM series, and it's the HFM50, which is 50 millimeter opening. So there's a 100 millimeter opening and a 50 millimeter opening. The additional capabilities you can add to it are a high thermal conductivity kit, which extend the range up to 2.5 watts per Kelvin, as well as the ability to measure specific heat. And that's actually an example of a specific heat measurement by the heat flow meter on the screen. Coming to the other side, typically we would have our MPV here, but it's on its way to a show. That will be back in the demonstration corner in the future, of course, but we use these instruments for various purposes. So typically there would be our MPV, which is our measurement platform, versatile. You'll have to visualize it here. It's our mid-range measurement platform combining multiple methods, transient plane source and transient hot wire for solids, pastes, and powders for thermal conductivity, thermal diffusivity, and specific heat. We certainly have a lot of demonstrations on that instrument. This is our focused THW-L1 for measuring thermal conductivity, thermal diffusivity, and specific heat of liquids and phase change materials according to the appropriate standard. And this is our HFM25, which is our baby heat flow meter for measuring insulation, but in a small format. This is a typical small sample, but of course it can do much larger. The maximum opening is 1 inch. So we developed this really because of the overuse of transient methods for measuring small format insulation. So we developed this to be able to measure with a more suitable method for such materials. This is our TPS3. We'll be doing demonstration on this over time. This is our portable transient plane source for measuring thermal conductivity, thermal diffusivity, and specific heat. It does allow you to buy sort of two parts, the basic package to use your own Keithley, or you can package it with the Keithley, and that's the 2401. Its range is from 0.03 up to 70 watts per Kelvin. So that's our TPS3. And then our MP2, which is our baby measurement platform, our entry level. This combines multiple sensors that are designed for solids, pastes, and powders, all absolute in terms of absolute measurements, so high accuracy, but with more narrow range, operated off battery or wall power. So it's a great entry level instrument with all the same theory followed by all of our laboratory instruments, just with a smaller range. That's a bit of an explanation. So coming back to our MP1, today we really want to focus on sort of this package. So what we did is we stripped away the temperature platforms. We didn't want to talk about some of the other capabilities, but as a summary, I always walk into the MP1 of what's unique about the MP1 controller. The MP1 controller has 4 channels. You can kind of see or partially see maybe these 4 boxes, but they actually represent how many channels are available. So there's 1 channel in the front, 3 in the back. What does that mean? That means you can run a sensor or multiple sensors at room temperature. Here we have 2 sample setups, 1 plugged in the front, 1 plugged in the back. But if you look at some of the other demonstration videos, you'll see there's other devices sitting here, and that's the additional capability, depending on the method you package with your MP1, to measure with temperature. So why is that important? It takes advantage of the clever software to automate 1 controller to allow 4 channels to really increase your volume and simplify analysis. So typically, if you look at other instruments that are using an oven, the instrument is locked up until your temperatures runs are complete. This allows you to have almost 4 instruments side by side and take advantage of 1 channel doing one thing and allowing the other channel to do another thing. So some of the other methods that you can add to this, in addition to the transient plane source, following the ISO 22007, are transient hot wire for measuring thermal conductivity, diffusivity, and specific heat of liquids following the standard, as well as transient line source following ASTM D533422A, and transient hot strip, which is a unique sort of square sensor that allows you to measure some unique capabilities of more rectangle type samples. It allows you to get down to 3 dimensions. So depending on your configuration of samples, that's the transient hot strip. So there's actually 4 sensors / methods that are available for the MP1. Today, what we're going to talk about is this setup, which really is an extension of one of the very high-level proprietary capabilities of the MP1 when you're using the transient plane source method. And that's our ability to characterize or measure the thermal contact resistance between the TPS sensor and the sample. And why is that important? It's because it characterizes the portion of time that represents the heat traveling through a layer of kapton, which is the sensor, a layer of contact resistance, which exists in every sensor to sample configuration and into the material. So by characterizing that region, you don't have to manually select it. That's one of the key capabilities. So when we were looking at how do we evolve the transient plane source method beyond where it's been for the last 15 years, that was one of the key areas. Like, how do we help the users define good data better? And up until this point, you typically would just visually manually remove those points. So by being able to characterize them, you can apply that correction and not have to do that. Now, in all of the added technology we've added to the transient plane source method, or any of the other methods, we still have the full capability of running everything manual. That's very important for us for keeping a deep understanding of your materials if you need to do that. So if you need to go beyond general characterization, because there are some unique capabilities of manual analysis, but we want it to be able to offer both. So advanced measurement, in terms of automating, and that's that element of the ITPS, which is the intelligent transient plane source, that design element that we keep adding to the instrument to take it from a manual approach to really fully automated testing and analysis. So we took that same capability and further developed it into sort of two separate testing modules. And what is a testing module? It's a variation of the principal approach of transient plane source. In this case, it's a variation of the one-dimensional heat flow method that's within the TPS method. And one of those modules is the transient resistance. So what that means is we're measuring the thermal resistance, and we've extended that from sensor to sample to between two materials. So we've packaged that with our basic TPS sample holder with a few basic additions and two standardized materials, which are stainless steel with, always the same finish. And what we're doing is we're measuring through primary or piece A into secondary or piece B. So anything you introduce between primary and secondary, which these are standardized materials, we measure the thermal resistance of. So if you introduce, actually this is designed for adhesives, thermal interface materials, coatings, and freestanding films. Anything you introduce between this, you get the thermal resistance of. So both of these, piece A and piece B, are treated as part of a series of resistances that we're measuring into, and there are quality indicators. Piece B is treated as an unknown, so when you're measuring your data, you can verify that you have a good sound experiment by achieving acceptable data of specific heat on piece B. So measuring through piece A, through a contact resistance, or introduced material, and into piece B, there's lots of ways of determining that if you have a good set of data. All of that applies to the next thing we're going to talk about, and there are quite a bit of, we've got previous demonstrations on our standardized package for transient resistance thin film. We got other demonstrations we'll be doing more in the future. There's an upcoming webinar on it with more theory, but what we wanted to do is make that capability available for measuring the materials we aforementioned, which is adhesives, tapes, freestanding films, and coatings. Make it a rather basic setup that's easy to afford and easy to use. But we want to introduce more variables, which is why we have this module. But before I move on, what are the reasons we did that? Why is this a unique capability? Is first, the ability to measure thin films and adhesive type materials is quite complicated with the available methods on the market today. They're narrow in range and can be quite sensitive to variations. Because you're measuring, typically with all those other methods, you're measuring direct thermal conductivity, which can be sensitive to variations. Or if you look at ASTM E1530, which I mentioned before, or the sister method for measuring thermal interface materials, and similar ASTM D5470, those do a pretty good method. They take a sound approach to the measurement, but are slow. They can be sensitive to improper setup, and a little bit complicated depending on how thin your material is and how many layers you need. You typically need 3 thicknesses, but even within each one of those thicknesses, you might need a minimum total thickness of multiple layers. With the transient resistance thin film, which is this package, we generally only need either, if your material has good, if it's like an adhesive or a tape, generally we only need to test 1 layer because the resistance between piece A and piece B is quite good. Then the intrinsic thermal conductivity of that material matches the calculated thermal resistance. It behaves like a liquid layer. If it's a freestanding film, of course that's not the case. In a freestanding film, if it's doesn't have a soft surface, that's the exception. If it has a soft surface like paper, you generally can test one layer. But as you get more rigid type freestanding materials, you can measure 1, 2, and 3 layers, but only 1, 2, and 3. And this measurement only takes about 5 to 40 seconds, depending on the height of your sample and the thermal resistance that you introduce between those 2 materials. So what is the advantage of that? You're only testing a very small sample and only 1, 2, and 3 layers of each. So it has many advantages in that. So it's rapid, easy to set up. It's using a basic system that gives you much more capability to measure in other types of materials, both for bulk and other. But it extends the use to a really high confidence, because when you measure 1, 2, and 3 layers of resistances and plot those, and the 1 over the slope is your thermal conductivity, because you're with the additional layers, you're backing out the contact resistance between the samples and the 2 materials. That's for rigid materials. You get a really high confidence values, because that change in resistance with thickness should be linear. So it's a little bit of a deeper explanation than I probably would have done normally on thin film, but everything I talk about here moves over here. So this is a basic setup. What makes it basic is it only has 1 pressure. So if you want to change various pressures, if you want to look at different influences of temperature, etc., this is a little bit more limited because it only has 1 variation. So we took that same capability and extended it into another module called transient resistance contact analysis. So it can measure freestanding films, adhesives, as well as thermal interface materials and coatings, etc., in every way this can. So single layer, multi-layer, looking at all those variations, but with introduced variables. And those variables are, instead of doing similar materials, you can do similar materials but also dissimilar materials. So piece A and piece B can be metals, similar metals, or dissimilar metals, or in this case we have steel and aluminum, and then you could have different finishes. In this case we have aluminum and Delrin, again with different finishes. So we can vary the materials. You can vary the surface finish, as well as vary the compression, as well as, in this basic setup, this is room temperature, you can also vary the temperature. So the temperature that the sample is sitting at. And of course, contact resistance, in this case we don't have to introduce a material, so we can measure the dry contact resistance between 2 materials. So you can measure introduced materials and get the resistance of those and calculate the intrinsic thermal conductivity of that introduced material in these application or applied setups, or you can measure the effective value of 1 layer. So let's say you have an application and you're looking at an adhesive or a film and you want to introduce it between 2 specific types of materials with specific finishes with a certain pressure or temperature. You can see its true performance in that application versus its intrinsic thermal conductivity, which most likely is different than the applied thermal resistance due to those same variables that are introduced from the application. So today we're gonna do a measurement on stainless steel, piece A. So this is your primary piece. It's 3 millimeter piece of stainless steel. We've standardized the diameter to 21 millimeters. Of course, we can vary that diameter based off the application, but this is our standardized dimension. Piece A is polished. piece B is the same stainless steel, so we're doing similar materials with a sandblasted surface. So hopefully you can kind of, if you put them side by side, hopefully you can kind of pick that up. And these we've measured the surface roughness. That will probably work its way into a paper someday, but today we're going to do this configuration symmetrically. I'm going to do a sample setup. This is our compression stand. You can vary the height of your samples, and we're going to do 5 pounds of pressure. We've already before this measured that same setup with 30 pounds of pressure, so we'll be able to compare the dry contact resistance between piece A and piece B of a similar material with polished and sandblasted surfaces together with 2 different pressures. And then we have some data to show on 2 pieces of polished under various pressures. So we have a curve of a variety of pressures on the same material. And then we have some data on dissimilar materials with different surfaces, and you can see how they trend in terms of thermal resistance. Why is the thermal contact resistance between 2 objects important? In addition to understanding how an introduced material behaves or performs, so its thermal resistance in the applied application. In addition to that, just measuring contact resistance between 2 objects. Why that's important is many times in design of simulations, thermal simulations, the thermal contact resistance between 2 objects under different variables is unknown. So that's a rather significant potential area of importance depending on the variables that you're trying to achieve. We hear a lot of customers describe that. So this is an important capability for those types of applications to understand how the materials react together and the contact resistance between them, so that data can be transferred through to simulations, so the simulations can be more accurate. So our setup, so if you want to bring the camera in a little closer, we're going to do polished and sandblasted on the bottom. So we're going to line that up. I'm sorry, my hand's in the way. And then we're going to do the same symmetrically, so polished and sandblasted. And this is stainless steel. And we're just going to, I'm trying to not put my hands in the way, but it's hard to do. So we're going to make sure those are well aligned with the sensor. The sensor is almost identical to the same diameter of our one-dimensional shapes. So that does make it somewhat easier to set up, because any exposed sensor you would see. And we're going to apply roughly 5 pounds. Doesn't have to be precise. As long as it's different than the previous 30, it gives you an example of 2 different. So that'll do a little bit of relaxation. That's roughly around 5 pounds. That's our setup for room temperature, 5 pounds, similar materials with different surfaces. So there's other videos that show sensor setup and etc. So we're just going to focus on contact analysis. And now I'm going to go over to the software and we'll do an experimental setup and run a measurement. So we've already previously filled out the fields, 5 pounds. Substrate height, that is the primary sample, it's 3 millimeters. The surface area of the one-dimensional shapes, and then the film thickness. In this case, we've not introduced any films. It's only the surface roughness. So we're going to put 0. Port 4 is what we're using, so that sensor and sample setup is plugged into port 4. All of these experiments use the same diameter of sensor. We're going to check the sensor for resistance. Not just make sure that the sensor is electrically connected properly. Excuse me. That's okay. The test times are very few because the heat is, we just want to make sure we're penetrating through primary or piece A, through the contact resistance and into piece B or secondary. So we'll leave it at 5 seconds, and pretty much all of the measurements are standardized roughly around 1,000 milliwatts. We'll do a quick transient, and then once we generate that data, we'll open it up in the analysis app and analyze it to give you that resistance value and compare it to the 30-pound version. We can run a quick transient to achieve that goal. If we were going to fully, well actually we will, before we close out the demo, we'll set up a schedule of 5 measurements, and you'll see that sort of show up in the right-hand side of the experiments. And that will make sure that we're running an experiment with the required delays between each measurement, that we're getting really high confidence data. The quick transient is really a quick way to generate data, to have a view of it, and to make sure that everything is set up the way you want before you invest the time in a full schedule. But in this situation, demonstration, it does work. It does work to achieve quick data. So right now, if you were to see the front of the instrument, you would see on the display screen, you would see it say balancing the bridge. It has a Wheatstone bridge internal, which is according to the ISO. And once it's done the balancing bridge, it'll go into the 5-second measurement. So what's happened is there's a current being supplied to the sensor, which generates heat. Due to the one-dimensional heat flow, that heat will travel down the lengths of those, symmetrically, down the lengths of those materials. That measuring can be done asymmetric as well. I do get the question is, why don't you insulate the material? These materials are conductive enough that heat takes its simplest path, and actually air can be okay insulator. In this case, because these are metallic, that is the case. If you were to do as you decrease the conductivity lower and lower and lower, you might benefit from some passive guarding, some insulation around those rod-shaped materials. But with these more conductive materials, it's not necessary. So there's our curve. We will just close that and open that up in our analysis. So before I look at this data, I'll describe what this application is. So we have separated software into sort of two instruments. This is our data acquisition, which controls everything that's connected to the controller. So it generates data, and you can review data and schedule everything. That's what you see. If we had multiple devices, they would all be sort of populated along the right-hand side. So you can experiment, layer over another experiment, layer over another experiment, etc., etc. So, and we've separated the analysis of the data that the instrument can generate, and it can generate a lot of data, into transient analysis, which lets us have a lot of special features and very unique capabilities that you can't get when you stuff it all into one application. So let's open up the 5-pound version of this experiment. Again, we've only made one measurement. And so here is our 30 pounds. And what you see populated in this summary table is the properties of the secondary material. So that's this being stainless steel. That's a measured property, volumetric heat capacity and thermal effusivity, and that's a very good value for an unknown property on secondaries. That gives me a lot of confidence in, when I click the individual row, that gives me a lot of confidence in the resistance that it measures across piece A to piece B. So that is the measured material. If we had introduced a film in there, the film would be the resistance, but because we have no film, it's measuring dry, right. And that's at 5 pounds. Sorry, that's at 30 pounds. And you can see the repeatability as I toggle through one measurement through the 5. So 0.23, 0.229. We'll just show the rest of these so you can get an idea on the repeatability of that setup. So that gives you an idea. And if you export these all to Excel, this is all summarized, all the properties. We just try not to put too much data all in one place, when Excel is a nice way to review that. So if we compare that 0.23 at 30 pounds to the same experimental setup at 5 pounds, you would expect the resistance to be greater, which it is. So it's 0.26. So that's the contact resistance between stainless steel and stainless steel when one surface is polished and the other surface is sandblasted. So what we'll do is we'll set up an experiment with a schedule. So all of these were good. We'll do a measurement of 5 with maybe a 10-minute delay at 5 seconds and 1,000 milliwatts. And we'll just start that, and the instrument will just start developing data. And this is your centralized data acquisition screen. It gives you all the steps of what was previously measured, and you can select, sort of see what each one is standing for. So that is a summary of 30 pounds and 5 pounds on that same experimental setup. But we have a couple other examples to show, and as I had previously mentioned. So this is stainless steel, polished against polished, so the exact same pieces, just polished on both sides. And so obviously where it's polished, you can see right away that one of those measurements we just made, which was 5 pounds, this is a much lower thermal resistance because that's polished against polished, not polished against sandblasted or rough. So you do have a lower, you have a lower resistance due to that very phenomenon. But as you can see, with the change in pressure, excuse me, with the change in pressure, you have a decrease in thermal resistance. So that's a pretty interesting capability, only up to 20, but that gives you an idea of thermal resistance versus that application. So you do see a trend of decreasing thermal resistance, and as you get to a higher pressure, of course, the change is less. That all makes sense, especially for materials that are rigid and not compressible. So we go to dissimilar materials, and I'll explain this a bit. This is on the left-hand side, primary samples that we introduced against various secondary samples. So piece A or primary versus secondary or piece B. So stainless steel, 3 millimeter thick versus Maycore. Again, that's the sample that's first, 1.5 millimeters thick in aluminum. And what we did is compare the finishes, the native finishes that were on each of those, to smooth and rough steel, smooth and rough Maycore, and smooth and rough Delrin. And we actually have the surface roughness measured for each of these directly, so there's a very good correlation between the change in surface roughness versus the change in the thermal resistance. But just to simplify this table, that's what we did. So in Maycore, you have the same thing where we measure it against each of these variations. So for each piece B, we have a smooth and rough. And in all the trends, you can see that there's an increase in thermal resistance with surface roughness. So same piece A, you have an increase of thermal resistance when your steel is smoother rough, or Maycore is smoother rough, and Delrin is smoother rough. And if you even look at a magnitude of change, obviously the intrinsic value of the material versus the surface roughness can have a difference. It's not necessarily always going to be the same percentage. Even if they're the exact same measured surface roughness, the thermal resistance can vary because the hills and valleys created by the roughness, if the intrinsic properties of the material that are the hills of the hills and valleys, it's going to create different thermal resistance values between two materials. So this is to create a conversation. Probably this will show up in various forms based off of the configuration of your material and how you're going to use them. But we really want to sort of create a conversation around all the different variables you can introduce. The one variable we haven't shown you here is the introduction of temperature. So measuring some of these phenomena with temperature to really map out a full understanding of how a material changes with all of the differences. What I encourage you to do, if you're interested in measurement of contact resistance between two objects, or measurement of effective value of a material introduced between two similar or dissimilar materials, and you want to see the effects of that application, is get in touch with us, and we'll really talk about what your two materials are, whether they're one-dimensional shape or other shapes, we can usually deal with them, and what the pressures are, what the temperatures are, the operating temperatures or the application temperatures, to really understand that and make those measurements. We've done a lot of these measurements and provided that data, which has been of great value to increasing the certainty of the thermal simulations that the data is used in. So that was a bit of a longer one, but there was lots to introduce. Get in touch with us if you have any questions. Otherwise, thanks so much for joining us, and we'll see you on the next demonstration corner.